Good morning, class. Today we are going to continue statistics, moving into statistical applications. And we will start with the normal distribution. All right, so we saw last week about different ways to display data, one of those being the frequency histogram. So if we look at the one here on this slide, it looks like both the mean and median will fall in the modal class of 60 to 70, right? So this bar right in here, right? The shape of the distribution is approximately symmetrical about the mean, median, and modal class. So as you can see, this being the center, it's somewhat symmetrical. As the class intervals become smaller, the frequency distribution may look as follows. All right, so we break down the classes and make them a little bit more exact. And if we continue to do it again, all right, you can see that this now starts to resemble what is called the bell curve, which is a normal distribution curve. In a normal distribution curve, the mean, median, and mode all coincide with the bell's peak. Its height and width will depend on the spread of the distribution. The greater the spread of the distribution, the shallower its peak. Similarly, data that has a little spread will have a more pronounced peak. Right? And basically, when we're talking about spread here, we're talking about standard deviation, which is a measure of dispersion that we studied last week as well. All right, so in the normal distribution below, 1 represents the height of 200 students chosen at random in a school. The other represents the height of 200 students in 1 year of the same school. All right, so which one do we think would be which? Right, of course, we just read on the last slide that the less spread out the data is, that the higher the peak will be. So obviously, 200 students from 1 year at the same school would be significantly less spread out than 200 students from an entire school. Right? Students in the same grade tend to be closer in height than students spread out across multiple grades. All right, so the 68, 95, and 99.7 rule. All right, this has a few different names. It's also kind of referred to as the empirical rule, but just to kind of show you what it means. All right, so if we have a normal curve, something like this, right? So my median would be right here, mean, median, and mode actually. We call that mu for mean quite often. All right, now, regardless of what the shape of your peak is, all right, your standard deviations will still all kind of be spread out the same, right? So we have 1, 2, 3 standard deviations, 1, 2, 3 standard deviations, all right? So basically 68% of the data, all right? Now, if you consider the area under this curve to be 100% of the data, right? If you cover the entire, like shade in the entire area under the curve. Well, if you go just look at one standard deviation, within one standard deviation of the mean, so one standard deviation to the left and one standard deviation to the right, this whole area here will be 0.68, or 68% of the data will fall within one standard deviation of the mean. All right. Within 2 standard deviations of the mean, all right, so 2 standard deviations to the left, 2 standard deviations to the right, this whole area here will be 0.95, or 95% of the data should fall within 2 standard deviations of the mean. And of course, I'm sure you can guess by now what that last 99.7 will be, right within 3 standard deviations of the mean, 0.997, or 99.7% of the data will fall within 3 standard deviations of the mean. All right, so very little data falls outside of 3 standard deviations of the mean, and typically those are outliers for the most part. All right, so the lengths in centimeters of a certain type of snake are recorded. It is found that the distribution of the lengths follow a normal distribution with the expected value, which is the mean, of 125 centimeters and a standard deviation of 10 centimeters. All right, draw a normal distribution curve showing the data above. All right, so we'll start there. So we're going to start with a bell curve. All right, and then we have 1, 2, 3, 1, 2, 3. All right, so if the mean is 125, that will always go in the middle. All right, and then my standard deviations are 10. So this way I'm going up 10 each time. So 135, 145, 155. And here we would have 115, 105, 95. Now, a snake is chosen at random from the population. What is the probability that the length is less than 138 centimeters? All right, so 138 centimeters would be over here somewhere. All right, so basically what we want to find is this area underneath the curve. All right, and we can use our calculator to do that. All right, so let's go ahead and pull out our calculator here. All right, so what we're going to do is, if you see this vars button, which stands for variables, up above that in blue here, we see DISTR, that stands for distribution. So if you hit second vars, you'll get all of these random distributions. All right. For normal distribution, we are going to be using normal CDF, which stands for the cumulative normal, essentially. All right, so I'm going to hit that. All right. Now, the lower bound, all right, is basically some number way out here to the left of whatever area we're looking for. All right. Now, obviously, this was like 95, so we could go anything significantly less than 95. Of course, you can also just think about it realistically, right? What's the shortest a snake could actually be? Well, I'm just going to put 0, right? Obviously, you can't have a 0 centimeter snake, but you certainly can't have negatives. So, and then we go to upper, right? Well, the upper that I'm looking at here is this dotted line here, which we know is at 138. Right, mu, this Greek letter mu, is my mean. So again, if we come back here, the mean is 125. And then this is sigma, which also stands for the sample standard deviation. So we know that our standard deviation is 10. Now, if you have an older calculator, sometimes you just have to type it in like this, right? Like with the newer calculators, it kind of prompts you and gives you all of those things, and you fill them in, and then it automatically pastes this to your screen. If you have an older calculator, when you hit normal CDF, it'll just bring out this normal CDF command with the parentheses, and then you have to know that you have to put lower bound, comma, upper bound, comma, mean, comma, standard deviation. All right, so when we do that, we get 0.903. Remember, in IB, we typically go to 3 significant figures unless prompted otherwise. So 0.903. All right, so when it asks what is the probability, you can actually give the probability as just a number between 0 and 1. That's perfectly fine. Or you could think of this as 90.3%. Right? So there's a 90.3% chance that any snake chosen at random is going to be less than 138 centimeters. Right, if you go to page 164 in your textbook, right, it gives you the breakdown on what I just showed you with the calculator, how to use it to find a normal distribution. All right, so now we'll talk about inverse normal calculations. All right, so we just did a calculation where we had to find the probability of an event happening. All right. The probability relates to the area under the relevant part of the curve. It is important, though, to be able to work backwards. These are known as inverse normal calculations. And you'll kind of see what we're talking about here in a moment. All right, so an example of that. Right, the heights of a group of boys are normally distributed with a mean of 175 centimeters and a standard deviation of 7 centimeters. Right, the college basketball team is looking for new players. It is only considering the boys whose heights fall in the top 10% of the population. All right, what is the minimum height that a boy must be in order to be considered for the basketball team? All right, so just as a visual, and as it says here on page 167, it has directions on how to do that. All right, but just for a visual, all right, we're dealing with the normal curve, and basically we want, we know that this area here is going to be 10%. All right, so we want to know what this number is. Okay, now we know that the mean is 175 centimeters, and that the standard deviation is going to be 7, right? So each one of these tick marks, you would go up 7. Each one of these tick marks, you would go down 7. So we want to know what this number is right here that will give us the top 10%. All right, so again, we can go back to our calculator. All right, we hit second vars to get back to our distributions again. And this time we're doing inverse norm. All right, now it's important when it says area, even though we're looking for this 10% area, the calculator always wants the area to the left of whatever number we're looking for here. So if this is 0.1 or 10%, then the area to the left of that has to be 0.9 or 90%. All right. So the area here is actually going to be 0.9. All right, my mu, we said, was 105 centimeters, the mean. All right, the standard deviation, they said, is 7 centimeters. With the new calculators, I guess, you don't always have to go to the left, but that's only with the super new operating system. Most calculators, including all of the ones that we use in our classroom, force you to do the left. All right. So if you have one of the new ones, we could have put 0.10 and then put right, and it would give us the same thing. All All right, so 183.97, again rounded to 3 sig figs, that would be 184. So this would be 184 centimeters. So they will only consider you for the team if you are at least 184 centimeters tall. Okay, so that's normal distribution. Now we're going to go ahead and move on to scatter diagrams, bivariate data, and linear correlation. When we record information about two different aspects or variables of a data item, such as height and mass of children, or temperature and number of ice creams sold on particular days, we are collecting what is called bivariate data. We can use the value of the two variables for a data item as the coordinates of a point to represent it on a graph called a scatter diagram, or scatter plot. Scatter plots are particularly useful if we wish to see if there is a relationship between the two variables. How the points lie when plotted indicates the type of relationship between the two variables. Hopefully we've all seen scatter plots before. All right, so here we have an example. The heights and weights, which are masses in this case, of 20 children under the age of 5 are recorded. The heights were recorded in centimeters and the weights in kilograms. All right, so A, plot a scatter plot for the data above. Comment on any relationship you see. Okay, so I'm not going to plot this by hand because that looks a little messy. All right, so I'll go ahead and pull out our calculator again. All right, again, we're going to go back to this stat button that we used last week and enter to get to our lists. So I'm going to put the height in list 1 and the masses in list 2. So 32, 34, 45, 46, 52, 59, 63, 64, 71, 73, 86, 87, 95, 96, oops, 96, 96, 101, 117, and 121. Alright, so now I will put in the mass of these children in kilograms. So 5, All right, so now all of our data is in. All right, we're going to have to do a couple of things here, just like we did last week. We're going to go to stat plots here. We're going to turn the first one on, and the default is a scatter plot. All right, and this is just saying, okay, my L1s are my X's, my L2s are my Y's, and then you can put whatever you want, you know, uh, to represent those data points. All right, so now we want to go to window. All right, my lowest height is 32. We can just go from 0, that's perfectly fine. All right, our highest or largest height is 121. So we'll just say something significantly bigger just so we can see the whole graph easily. Scale, we can go by 10s here, should be sufficient. All right, my Y's, my lowest Y is 3 point something. We can just go from 0. My largest Y is 20.895. So we could say 25 if we wanted. Y scale of 1 is fine. You could go by 2s. In fact, let's just go ahead and make this 30, and then we can go by 2s. So now when we graph, right, there is our scatter plot, right? And it says to comment on any relationship that we see. All right, well, you know, it's pretty obvious to see that as our heights get larger, our masses get larger as well, which makes sense, right? Somebody who's 6 feet tall is going to weigh a lot more in general than somebody who's 5 feet tall. So as you get taller, you should weigh more. All right, the scatter diagram shows that there is a relationship between the two variables. We can use a line of best fit to estimate the value of one variable given a value of the other variable. To do this, we draw a straight line passing through the data. All right, it will pass through the point x bar, y bar, which is the average of the x's and the average of the y's, and leaves approximately half of the points above the line and half of the points below it. It does not need to pass through the origin. All right. So using the data about the height and weight of children in the previous example, estimate the weight of a child with a height of 80 centimeters. Okay, so if we look at this data, all right, 80 centimeters, these were by tens, so 10, 20, 30, 40, 50, 60, 70, 80. So right up in here somewhere. All right, now we would want to draw a line through here, okay, which is going to be hard for me to do. Let's see if it'll actually let me add it here. There we go. All right, so now I can draw some line of best fit. All right, and actually, just to be a little bit more precise, I'm going to jump a little bit ahead here and show you something. We kind of did this with one variable last week, but we can do it with two variables too. So I can go here to stat, go over to calculate, and we can go down to two variable stats instead of one variable stats. All right, so now it'll do x's and y's. So here my x bar is 77.75. And then we can look at the y bar as well, and it's 12.535. All right, so this is in tens, so 10, well, actually 20, 30, 40, 50, 60, 70. This would be 80, so 77.5 would be somewhere in here. 12.75 on the Y scale, we're going by twos, so 2, 4, 6, 8, 10, 12, 5, 3, 5, so somewhere right in here. Alright, so now we can just draw a line of best fit. Alright, it has to go through this point, and then we want roughly half of the data above and half of the data below. Sometimes you can't get exactly like that. Alright, but this is a an acceptable line of best fit. Alright, so if we wanted to estimate the weight of a child with a height of 80 centimeters, so we would go here, 20, 30, 40, 50, 60, 70, 80. All right, and then basically we want to say, okay, well, where would that meet my actual curve? And we come over here, so 2, 4, 6, 8, 10, 12, 14, just about 14 kilograms. Right, your graphic display calculator can plot scatter diagrams, which I just showed you how to do. For example, plot the following data for an ice cream vendor on a scatter plot, and if appropriate, draw a line of best fit. All right. I'm not really going to go through that since I just showed you how to produce a scatter plot on the calculator. Now, in a minute, we'll get to how the calculator can actually get you a extremely accurate line of best fit, but we'll get there. All right, so there are several types of correlation depending on the arrangements of the points plotted. All right, a strong positive correlation would just be as but if we just have a bunch of dots and it's very obvious that as my whatever my x variable is here increases, then so does my y value, and that the dots are nice and compact and close to each other, right? That's what we consider a strong positive correlation. All right, a weak positive correlation, where the dots would be a lot more spread out, but still, in general, like as the x variable gets higher, the y variable does too. It's just not quite as tight and compact, and it's not quite as cut and dry, right? Like some of these things, like still can be a little bit lower than what you might expect them to be. A strong negative correlation, again, the data points would be nice and compact and close, but this time, as the x variable gets larger, the y variable gets smaller, right? So if you kind of drew a line of best fit here, it would have a negative slope. As, of course, if you drew lines of best fit for these two things, the lines would have a positive slope. That's why we say it has positive correlation. Of course, a weak negative correlation, again, the dots are just a lot more spread out, but still, as my x variable gets larger, in general, my y value gets a little bit smaller. All right. There's also one that we kind of missed. You can also have basically no correlation. All right. And that's basically when you just have kind of dots all over the place, and there's no necessary like rhyme or reason, right? doesn't matter. Like just because my x's get larger, it doesn't mean that my y values get larger or get smaller. There's just really no relationship between them. All right, Pearson's product moment correlation coefficient. Carl Pearson was a statistician and one of the few mathematicians who launched a totally new field. In his case, he joined zoologist Walter Weldon to study what he called biometry. That is, he applied statistical analysis to animal evolution, among other areas. Pearson's product moment correlation coefficient, which we will call R, measures the correlation between two variables x and y. Right, the range of values for R is between -1 and 1. Right, where -1 indicates a perfect negative correlation. Just excess there. Right, 0 indicates no correlation at all, and 1 indicates a perfect positive correlation. The value for R can be calculated by the following formula. R is equal to S sub xy over S sub x times S sub y. Right, where S sub xy represents the covariance, how much two variables change together. And this, if needed, is almost always given on an IB test. S sub x represents the standard deviation of the x. Now, do be careful that in our calculator, right, we use this to represent S sub x, although there is an S sub x in the calculator, but be mindful, we actually use this number. Same thing with y. Sigma sub y, or S sub y, represents the standard deviation of the y's. All right, so as I said here, you will always be given the value of the covariance, right, if the formula is needed on a test. However, it can be calculated using this formula here. So this is the sum of the products of each data point, right, the x-coordinate times the y-coordinate, all right, minus the sum of the x's times the sum of the y's, all divided by n, and then the whole thing divided by n. The only time you would really need this to use this is maybe in your IA, if you're trying to look fancy and show some mathematics. That's a good idea. The table below shows the position of a football team in the English Premier League and the goal difference. That is, the difference between the goals scored and the goals conceded. All right. So there is a lot of data. All right. If the covariance equals -77.14, calculate S sub x, S sub y, and R. Okay, so, and of course, we can use our calculator to find all of these. So let's go to our calculator. All right, we will go to our lists. I'm going to clear these out. Remember, hit clear, never ever delete. All right, so now I can put positions in here. So we have 1, 2, 3, 4, 18. And then our goal differential. 3. So there's our data. So again, we can hit stat, we go over to calculate, we do two variable stats, right? And we get that. Remember, although this says S sub x, remember we are using sigma sub x for my standard deviation. So 5.19 we will say. Right, our sigma sub y, which is the standard deviation of the y, is 15.25. Okay, so now we can use that formula for R, which is the covariance, which is negative 77.14 divided by 5.19 times 15.25. So if we do that in our handy dandy calculator, all right, so that is negative 0.975. All right, so it tells us to interpret the value of R. Well, remember, our R possibilities go from -1 to 1. The closer to -1, the closer you are to a perfect negative correlation. Closer to +1, the closer you are to a perfect positive correlation. All right, this is very close to -1. So this is a very strong negative correlation. All right, so now we'll start talking about the regression line for y on x. All right, so earlier we talked about lines of best fit and how you can just kind of eyeball them, right? Make sure that they go through x bar, comma, y bar, and then just kind of estimate the points, right? Try to get equivalent points above and below the line, right? However, there's a much more accurate line of best fit that is called the regression line, right? This line is the optimum line of best fit, right? And the formula for this line is this, all right? So y minus y bar is equal to s of xy. Remember, that's the covariance, which will be given to you on tests, divided by the standard deviation of the x squared, right, times x minus x bar, right? Now, guys, this is in point slope form, right? Because that was y minus y1 is equal to m times x minus x1, right? Where x1 comma y1 was a point on the line. Well, we know that our point on the line is x bar comma y bar. That's why this is x bar, this is y bar, right? And that means that this right here, the covariance divided by the standard deviation squared, is my slope. Right, the table below shows the number of hours 20 students spent studying Spanish in the month before the examination on their percentage score. All right, so A, find the correlation coefficient. All right, B, find the equation of the regression line. And C, estimate the score of a student who studies 30 hours in the month before the exam. Okay, now we could do all of that by hand, right? But why? All right, let's go ahead and show you how our calculator can do all of this. All right, so again, So I'm going to edit some lists. Again, I'm going to clear these out. All right, so Alright, so the hours of study are going to be my L1. Alright, and then their percentage score. So there's all of our data. Right. Now there is one thing that you need to do for your calculator to give you all of the information that we want. There's a couple of ways that you can do this. I like to just hit second 0 to go to my catalog, which has every single command that your calculator can do. If you hit D, this is D right here, it'll take you to the D's. All right. And what you want to do is go down to diagnostic on, hit enter. It'll take it out to your main screen. You need to hit enter again. It will say done. All right, so now you've turned your diagnostics on. All right, if we go to stat and we go to calculate, all right, now we want to go to this lin reg, ax plus b. All right, we hit that. The x's are in my L1s, the y's are in my L2s. All right, so now it kind of gives us everything. All right, so let's go ahead and take this here. All right, so now looking at what was on our screen here, all right, basically this is my R. All right, so R is equal to 0.73. I wouldn't call that super strong, but it's not weak either. This is a moderate positive correlation. All right, and then this y equals ax plus b. All right, doesn't that look a lot like y equals mx plus b? All right, so your a is your slope, your b is your y-intercept. All right, so this is telling me that y is equal to 0.863x plus 47.39. All right, so then it also says estimate the score of a student who studies 30 hours in the month before the exam. So all I have to do is plug 30 into here. All right, and when we do All right, so 73.28, so roughly 73%. And we are done with linear regression as well. All right, so for your homework, all right, just do all exercises from 4.1 through 4.3. All right, have a good day.